class. All right. So this is that same problem, but it's looking at as it's getting a lot longer, a lot more or boxes in there. So we start to get down, and as the limit, as they start getting smaller and smaller, so this was 10, and the area was 0.385. This was 30, and the area is 0.3502, then 0.34434, and then we go down here, it's 0.3234. So what's it getting closer to? 0.3333, it's 1/3. If we kept doing it over and over and over again and getting it closer and closer and closer, we would get, the limit would go to 1/3, which is my integral. So the integral of a function will tell you the area under the curve. Okay. Along with what the actual equation is and vice versa. But it actually, the big thing and the thing that's actually most useful is it gives you that area under the curve. What that's going to allow us to start doing is looking for area, which is great, but it also allows us to look for volume of shapes, which is one of the first things you're going to do in Calc 2. You're going to take actual functions and rotate them and figure out what the area is, or the volume of shapes is, or what the surface area of shapes is, stuff like that. So it allows us to do more organic shapes than what you can do just as simply in geometry. But all the formulas that you used in geometry class were derived from these rules. So all those area equations that your geometry teacher taught you, and they couldn't tell you how they actually came up with them, came up with them because of calculus. They actually use this to derive those, at least the more complicated shapes. The basic ones have been known for a while. All right, so we talked a little bit about this last Thursday. So that right there is my summation symbol. That goes to that elongated S. Because what we're doing is we're really summing the infinite number of those rectangles underneath the curve. The A and the B, that's the interval we're looking at. That could be any interval. It does not necessarily have to be 0 to whatever, it can be anything. Then we have the function, and this stands for the change in x, which you probably have seen things before as the delta x. Instead of using delta, we use the d. Same concept. Okay, that's talking about that change in that x, which, if you think about these curves here, the change in x is how big that width is. That's what the change in x stands for. So as the change in x it gets infinitely small, that change in x gets infinitely small, that's what the integration finds you. So that's what that change in x actually means, or the dx right there. All things, you don't really need to know how to solve the problems. The problems can be solved without knowing those. Just understanding why it's done that way is kind of important sometimes. All right, let's do a couple of problems. So, what was the integral of x squared? We just did this one. Was it? X to the third over 3. You write this like this. That's how you would write it. That line just, if you look here, those are the intervals. So I'm doing x to the third over 3 from 0 to 1. Because that's not my final answer. That's a step in the answer. Now I have to actually do those calculations. So we plug in 1 and we plug in 0. So you're doing basically the integral, the function there. So it's 1 to the third over 3 minus 0 to the third over 3, which is 1/3. some problems, the 0 gets rid of the problem. It doesn't always get rid of the answer. So you do have to do the 0 even if it's there, because it doesn't always eliminate that term altogether. Not everything to the 0 or with 0 in it disappears. Let's do this one from 1 to 2. All right, so what's the integral of x squared? It's the same thing. You don't necessarily have to do it again. We know it. It's x to the third over 3. But this time I'm evaluating it from 1 to 2. So that means 2 to the third over 3 minus 1 to the third over 3. You are always doing that top number minus the bottom number. So that goes there, and that goes after the minus. This is top minus the bottom. It is not always the biggest minus the smallest. We can go backwards. But it is always the top minus the bottom. So I have, what's 2 to the third power? 8. So I have 8 thirds minus 1 third, which is 7 thirds. And if I did 0 to 2, which I'll do really quickly. If you notice, the first two were the same region, right? 0 to 1 and then 1 to 2. 0 to 2 is the same answer. If I added the first two together, I'd get that answer at the end. So I could take my intervals and split them up to find the pieces of them. And it should come out to be the same answer. So this big answer here, I'll show you this. This is how the book wants you to do this. It's taking the integral, it's taking the limit of it and keep going with the limit. We're not doing the limit. Okay? But that's the limit way to do it. We're going to do it with integration. So, find me the integral of x to the third minus 6x. So we can do it in pieces. So what's the integral of x to the third? X to the fourth over 4. What's the integral of 6x? 3x squared. It would be 6x squared over 2, which is 3x squared. And we're evaluating it from 0 to 3. So I've got 3 to the fourth over 4 minus 3 times 3 squared minus 0 to the fourth minus 3 times 0 squared. That all ends up being 0, so I don't have to worry about that. 81/4 minus 27. Come on, y'all have to do it in your head now. That's kidding. Well, considering it's right here. 27/4 is 108 to the fourth, which ends up being negative 27. So, which way is easier? Integration, the way we just did it, is a lot easier than doing the limits. It's just like when I showed you the limits at the beginning before we did the derivatives. The derivatives were a lot easier than doing the integration because it combined a lot of that stuff. It did a lot of the stuff for us. That's what the operation does. So you do not have to worry about doing the limit method. There's no real reason for it. You will get shown it again when you're doing some of the other methods in Calc 2, but if the teacher forces you to do the limit method, I don't like them. So, all right, this was what that curve was finding. So it was finding the area down here and the area up there. This area down here would be what? That's going to be a negative area, right? And this stuff up here would be positive. That's why, if you looked at my answer was negative. So it found the area of the whole negative part and then subtracted off that positive part, basically. Okay. So that's how we get a negative area. When you typically would think of area, you shouldn't be able to get a negative one, but negative areas would be below the curve. You could do this one in pieces and find from that point to that point, find the absolute value of each piece. So this way you get a positive area. But you don't have to do it in the steps. You will later, though. When you do the area or the volume and stuff, you'll do that. All right. Here's a great example of, well, here's one example. So if we look at e to the x, so this is a great example of one that does not eliminate. So the integral of e to the x is e to the x. So we plug in 1 to 3. So you have e to the 3 minus e to the first, or just e. Because you don't have to put the 1 up there. If we did 0 to 3, e to the 0 is not 0, it's 1. That's why I say you have to plug in that 0, because you are not always going to get rid of it. A lot of times, very rarely are you going to have a constant at the end of an integral. Okay, there is certain situations where that can occur, but it is very rare. So in typical like polynomials and stuff, yes, the 0 is going to cancel everything out. You don't have to worry about it. But in other type functions like e, it doesn't. And some of the trig functions, it doesn't. Like cosine of 0 is not 0, it's 1. So don't just like, one of the habits that people get into is, oh, I see a 0, I'm just not going to worry about that part. Don't do that. As soon as you start doing that, you're going to come across the problem that you need it and you're not going to do it. So at least like make the effort like I did here. Like, okay, I know I plug in 0. Okay, I don't have to worry about that. It comes out to be 0, cross it off. But make the effort to look at it to make sure that that's the case. All right, some basic properties of integration. I can make it bigger for you. They're honestly pretty straightforward. If it's a constant, you're just it's going to be c times x minus that, so you don't have to necessarily worry about that. Addition, you can split up. Okay. do the integral of x to the third gives you that, and then the integral of negative x to the sixth, or negative 6x gives you that. Because sometimes that negative sign is going to disappear. And if you leave the negative sign, then you're going to have another negative sign, and it's really easy to say, oh, I already have the negative sign, I don't have to write it. Like, for example, if you did sine of x, if it was minus sine of x and you did the derivative or the integral of that, you'd get negative cosine of x. So you'd say, okay, I already got the negative sign there, I don't have to put another one. However, what's the integral of negative sine of x? It's positive cosine of x. So you'd have two negatives, and that would get rid of it. So it's a good habit to, even though it works either way, to put that negative sign on whatever you're doing the integral of. Constants, I actually showed you that the other day. You can pull out, so you don't have to worry about the constant. And there's the subtraction one that we were just talking about. Like I said, I would typically make an addition anyway. What's not there? Multiplication and division. You cannot split things up based on multiplication and division. There's other rules for that. Just like you couldn't do that for derivatives. We had derivative rules for product and quotients. Integration's the same way. All right, find me the answer. What's the integral? Without typing the answer, like plugging the numbers in. What do we got? What's the integral of 4x squared? There's half the class here. You have more opportunity to talk. What's the integral of x squared? X to the third over 3. And we have a 4 in front. So it's 4x to the third over 3. You are going to see a lot of fractions in integration. Okay? Fractions are not going to go away. There's going to be a lot of them. So don't assume when you see a fraction it's wrong, because you're dividing by something always. So what's the integral of x? What's the integral of 2x? Or 2x. And we're evaluating it from -1 to 2. All right, plug it in, find me the answer. 117 or what? Yeah. Almost. And I'll show you why in a second. Correct answer is 39 over 2. You can reduce it. So here's, again, I don't expect you to do this out by hand. So again, we can use Desmos. One of the nice things is you can type your equation in here and just plug the numbers into it. So if you plug in 2, you get 50 over 3. If you plug in -1, you get -17 over 6. And since I'm subtracting, I'm adding 17 over 6. Notice this little dot right here? You're typically going to get it as a decimal. If you click that little dot, it gives it to you as a fraction. And it will always give it to you as a fraction in the reduced form. Okay? So 39 over 2 would be the final answer for this one. This is the scientific calculator, not the graphing one. You can do this in the graphing one too. It just looks a little different. So I'll show you. So you can do that here. And then you can do x equals 2. Oh, actually, you can't do it that way. This one you have to do the table. But the problem is it does not give it to you as a decimal. I mean, as a fraction. It gives it to you as a decimal. So it's not as nice. But the scientific calculator always does that, which is very nice. So, and they have an app for the scientific calculator too. So, or just go to the website, click scientific. It's the exact same as the app, so you don't need to download it. So we had 39 over 2. Now, because these problems come out to be a lot more in fraction form than the derivatives and stuff that we were doing before is, I would rather my answer as a fraction than as a decimal, unless the decimal ends. Like 19.5 is the correct answer. It doesn't go on forever. It's fine. However, 17 over 6 does. So I would rather it as -17 over 6 than -2.832. Okay. So get in the habit of putting your answers as fractions. Now, if you had left your fractions that way, I probably would have taken off a point because you didn't reduce it. That didn't do anything. But you'd have gotten the fraction. There's two what's known as the fundamental theorems of calculus, and this is literally the end of what I'm going to talk about them for. The first one just says that the original function is if f is continuous and differential, the integral of the derivative is the function. And the derivative of the function is the integral. So you can go back and forth. That's what the fundamental theorem of calculus part 1 says. And the fundamental theorem of calculus part 2 says exactly what we've just been doing. You can plug the numbers in to find the final answers. You're never going to be asked, what is the fundamental theorem of calculus 1? Okay, it's not something you get asked. But these are the reasons all the things that we've been just doing is allowed, is because of these two rules. What is the integral from 0 to 2 pi of cosine of x? What do we get? Does that make sense? Why? Well, actually, it turns into positive sign. Cosine goes to positive sign. You do the derivative, which in this case didn't actually change the answer. Next one it does. But does that make sense? Like, we're looking for the area under the curve, right? Does it make sense that the area under the curve of sine of x is 0? Right. Because of the way sine works, it's symmetrical over pi, right? So the first half of pi is positive, the second half of pi is basically the exact opposite, negative. So they would cancel each other out. So that's one of the problems that we run into is sometimes when we're looking at these type of functions is that that's not necessarily what you want, right? That's not going to help you get any good information from it. So we would want to break down the problem in a way that we can figure out what the area is without getting 0. Okay, because that's not really helping me figure out what the area of the curve is. So yes, this one would be sine of x from 0 to 2 pi, which is sine of 2 pi minus sine of 0, which is 0 minus 0. 0. So you would break this one down. If we did 0 to pi, you also would get 0. Because sine of pi is 0. And sine of 0 is 0. Now that, there actually is area under there, right? Huh? Yeah. But when you're looking at, if you're plugging it in, what's sine of pi? Sine of pi over 2 is 1. It's 0. So even if I had done this one from that, you still get 0, which also doesn't help me. Because if we're like in the first one, we're like, okay, well, it kind of cancels each other out, right? Well, that's just that one curve. It doesn't cancel anything out. I actually have area there. So that's when you start to look at, okay, looking at the way that function works, let's start looking at let's break it down into pieces that I would actually do in problem 4. And if I did sine of x from 0 to pi over 2, I get sine of pi over 2 minus sine of 0, which is 1 minus 0, which is 1. And then if we did from pi over 2 to pi, of cosine of x, if you notice this one, we're going to get sine of pi minus sine of pi over 2 is 0 minus 1, which is negative 1. So if I add those two, I'd get 0, but we know it's not 0. We know it's 2. Because if you look at the curve, hold on, I'm messing this one up. We're not looking at sine. What function are we looking at? Cosine. That's what that was. I'm like, wait a second, something's off with what I'm saying here. So when we did this, that's the piece, that's that first one, and that's the negative one. So that's why it cancels out. It's still 0 because of the same thing with sine. This part cancels out with that part. Right, we're going back to the original function, not the derivative or the integral. So that's why that would be 0. But if we look at it, we really have an area here of 1, an area here of 1, so we actually have an area of 2. Same thing here. So the area under the curve for cosine of x actually would be 4. Because each of these spaces would be 1. Huh? Well, it would be, if you're looking at the area of the unit circle, it'd be pi r squared, so it would be pi, yeah. But you're not looking at the unit circle. You're looking at a calculation of the unit circle. So it's not, that area in there is not the pi piece. Like it's weird the way it works. It's not, so the area, the unit circle creates the value on the outside, but that's not the actual area under the actual trig function. Okay. It's the actual, because if you roll the actual function, it's actually the wheel rolled. So it's a point on the outside of the circle that's actually being rolled around. That's what's giving you the unit, the actual trig function. I had an animation of it when I did the trig. I don't now though. I think you took a picture of this last time. I don't think there's any new ones on here. That was the table of indefinite intervals. Do this one. That's a problem. Oh, that's what was I right? Oh, so close. Oh, well. You can do this with what you know so far. And that table. And yes, I'm coming around in a minute to see what you got. So try something. You're gonna need that. You can use that thing. One of those is gonna help you. Nothing up here that testing. That is not. We cannot do the integral of sine squared. Somehow we have to change the problem. Is that the same problem? What's that? That's cotangent. What's that? Cosecant. Cotangent, cosecant. So this becomes the integral of cotangent theta cosecant theta d theta, which equals cosecant theta plus c. That's when we need the plus c, because there's no numbers on the integral. So I have good news and I got bad news. Well, good news is for me. So I won a contest about a month or so ago, and got my art displayed in a place in Middletown. They're having their opening reception and everything else next Thursday, so I can't be here. So if you want to see, this is actually that's actually the art that I do. It's actually 3D printed. Yeah, it's all 3D printed. Feel like I do the design on the computer and everything else, and then I 3D print. Then I split it into a file that I can actually 3D print. So it's got texture and everything else. So I call it painting with plastic. It's fun. I enjoy it. So I've made some amazing art with it. It's really cool. For somebody who never thought I was going to be an art person, like being able to draw on a computer, it's amazing. But I have my thing sent next Thursday, so I won't be able to be here next Thursday. That was going to be the day for the review for the final. So we're going to finish chapter 5 tonight. I'm going to do the last piece of it right now. We will do the review. I will start the review. If we can finish it on Tuesday, great. If not, I will record a video and I will post it online for the rest of the review. So you will have the rest of the review on my website. That makes sense? Okay. Oh, I'll be here Thursday. Yeah, we'll be here this Thursday. What else? Hold on a second. Or was I a whole day ahead? I think I'm a whole day ahead. Hold on a second. Yeah, I know that. What other? Hold on. Like, I only got one section left. That's why I'm like, wait, what? No. I could do the review Thursday and Tuesday. Yeah, let's do that. So I'll start the review this Thursday, and I'll finish next Tuesday. So we'll be done. Okay. So yeah, that's it. No class CAs. If there's some questions and stuff that comes up, I will post those. All right. Thank you. I'm excited. It was my first actual like gallery type show. So everybody's like, and I'm like, I'm just a math teacher. It was my COVID thing. I was like, I was bored sitting at home. I'm like, all right, I got to come up with something to do. All right. Let's do. Before I do this one, is find me the derivative of that. I missed something. I missed something. I forgot the squared there. Otherwise, it's a really simple problem. All right, how do I do this one? What's the rule called? Chain rule. So what's the derivative of the inside? 2x, right? So that's the derivative of the inside. And what's the derivative of the outside if the inside didn't exist? So if I did 2/3 y to the 3/2, what's the derivative of that? We bring this down and subtract 1, right? So it becomes 2/3 times 3/2 y to the 1/2, right? So those two cancel each other out. And I'm left with 1 plus x squared to the 1/2. So 2x times the square root of 1 plus x squared. Correct? Okay. So if we look at that 2x came from right in there, right? Yes? Okay. If I wanted to go backwards, that's what this is. That's the integration, right? So somehow I've got to get that 2x gone because the 2x wasn't in my original problem. But then the 3x, the 3/2 and the 2/3 kind of work its way out, right? It's really just that 2x that's in the front that's there. And that's that piece there. So what we're going to do, this is known as U substitution. So we pick the thing that's annoying us, just like in the chain rule. So the thing that's annoying us is the thing underneath the square root, just like the chain rule. And we make that u. Okay, so the piece underneath the square root, the piece, just like the chain rule, the piece that's annoying us, that becomes u. We take the derivative of it. The derivative of u would be du. What's the derivative of 1 plus x squared? 2x dx. That means I did the derivative of it. So this side just becomes du. That side becomes 2x dx. Everybody good? Okay. Now comes the magic. That becomes square root of u. Everybody get where that came from? That's u. What's that? That's du. So it's the integral of u to the 1/2. We have to add 1 and then bring it down. Right. So it'd be u to the 3/2 over 3/2, which is the same thing as saying 2/3 u to the 3/2, right? And now we didn't start with u, right? So we can't end with u. We have to end with x. But what's u? 1 plus x squared. Hold on. Plus c. Exactly what I started with. This is the most complicated thing that we're going to talk about in Calc 1. But this is the number one thing you use in Calc 2. This thing is used a ton. And actually, it's the first thing you want to go to in anytime you get a complex problem, because it's easier than all the other methods you're going to learn in Calc 2. And honestly, it's actually pretty easy once you get used to doing it. So it's called u substitution. It is the inverse of the chain rule. So every rule that we did in derivatives is going to have a corresponding inverse rule in integration. This is the inverse of the chain rule. It'll undo the chain. All right, let's look at another one. Let's actually do one now that. All right, what's the annoying piece? What's the piece inside of something else? This piece, right? So just like the chain rule, that's the piece that we're going to look at. So if I'm going to make u x to the fourth plus 2. What is du going to be? This is the hardest part of this, is realizing when you're doing a derivative and when you're doing an integral. Right here, we're doing a derivative. So we're taking the derivative of x to the fourth plus 2, not an integral. Really easy to screw these things up. So what's the derivative of x to the fourth? X, okay, 4x to the third. I almost did it. And the 2 is gone, right? And don't forget your dx. So now the question is, so I can change that to u, right? But then I have x to the third dx left, right? I have that left. I can't have x's. I have to have u's. All u's. Do I have x to the third dx over here? Kind of, right? I have this extra 4 here that's annoying me, right? Can I get the 4 away? How would I get the 4 away? I divide. So 1/4 du is x to the third dx. So that becomes that. That makes sense? Or no? You're allowed to say no. The goal is to get everything that has x's in it to turn over to u's. So we took that one. That one's easy. This one right here, I had an extra 4, but I can bring it over to the other side. I'm not bringing an x back into it. I'm just moving the number. That 1/4 really is a constant, right? So I can take that 1/4 and just put it out in front. Because remember, constants I can pull out and put in the front. So what's the integral of cosine of u? Sine of u. So 1/4 sine x to the fourth plus 2 plus c. All right, try this one. It's not horribly important, but at your stage it is. Because when you don't have it, you're gonna go, what am I doing there? Almost. We can hear the word, was one half. Almost. Have it too. You're going to laugh your head, so I don't worry. Which is fine.
What do you see as the cards that exist?
I know. When you bring it over, what happens? Five more. Yeah. So when you break it out, this works. What's the annoying piece? Most people got this. That's the annoying part. So u equals 2x plus 1. So du is 2 dx. I don't have a 2 near the dx. I don't have a 2 out in front here to bring over. So I got to divide by 2. So 1/2 du equals dx. Now I have the piece to replace that. So integral u times 2 du. So the integral of, oh, sorry, not 2, 1/2. I saw too many 2's on everybody's papers. All right. So the 1/2 can come out. And I'm going to change that to a fraction so I can do the derivative or the integral. So the integral of u to the 1/2, this is the piece you had, is 2/3 u to the 3/2. So 1/3 u to the 3/2. So 1/3 2x plus 1 to the 3/2 plus c. Oh, you can get this answer almost right just by doing what you think is right. You're just gonna be missing a number. That was you've almost got it right. What's the annoying? Because otherwise, when you forget the dx, you don't know what you're replacing. And that's where you get lost. So that's the because that's what's going to get. Because I don't have a pod.
When I lose track of the year, I just go and look at it for a couple hours.
Almost. You walk there. You walk. It's you. That's the annoying part, right? It's that creative. Just use the dx. Like the dx here, I want the dx here. I gotta do this side over. That's why the dx is important, because if you don't have it, you're like, okay, what am I doing next? So it's like it's the little things in this that, like, when you get through Calc 2, when you start going through Calc 2 and going through a lot of the later sections that are a lot more complicated stuff, the teacher's going to tell you this is what's known as implicit substitution. Okay? Because you're not even going to want to do substitution. You're just going to do it without even thinking about what it is. And it sounds crazy right now. It truly does. I will admit that. But if you're like this problem right here, the u is 5x. So du is 5 dx. I need to move that over. So that becomes 1/5 du equals dx. So I'm doing the integral of e to the u, 1/5 dx, or du, sorry. So that's just 1/5 e to the u, which is 1/5 e to the 5x. All it is a constant or coefficient up there. The coefficient's always going to be 1 over that. So if I did integral of e to the 4x, that would be 1/4 e to the 4x. That's it. It's just the coefficient. Like this one, it was just a 2. You could have ignored the whole thing there and just pulled the 1/2 out and treated that as just due to the 1/2. And I know I was going to put a 1/2 in front of it because of that too. Those are the types of things that as it gets a little bit better, you're going to be fine. Right now, you're not there. And it's going to be a while before you're there. And it's going to be into Calc 2 before you're there. So right now, you cannot lose that dx. You have to have that dx there. Because once you lose it, then you're going to look at your problem and go, I don't know where I'm going. I don't know why I did this. Because you don't have anything to replace that with because you lost the dx. Okay? That's why it's those little things that really matter in the problem. Look at the table I gave you earlier. Because this looks like a really simple problem, right? Integral of tangent. Like we've done the integral of sine, we've done the integral of cosine. Look at your table. Is integral of tangent on there? not. It's not. It's not an actual simple integral. It's done now because it's actually, we need to do the chain rule to do this. What's tangent? What's another way to write tangent? So if I make u cosine of x, because I also don't know how to do division, right? So if you think about this one, the piece that, like, the division is going to be the annoying piece because I don't know how to do that. So if I make u d cosine of x, what's du? Huh? Negative sine of x. This, I will tell you, this is the one that you're always going to screw up. The x. We're doing the derivative, so it's down the list. It becomes a negative. That negative has got to come over to the other side. So it's negative du equals sine x dx. Do I have sine x dx in the problem? Yeah. I have sine x dx right there. So this becomes negative integral 1 over u du. What's the integral of 1 over u? Huh? Yes. ln of u. Because remember, the derivative of a natural log is 1 over x. So the integral is of 1 over x is ln of x. Don't forget the negative sign. So that means it's negative ln of cosine of x plus c. So the integral of tangent equals negative ln cosine of x plus the absolute cosine plus c. But you can't do that without the chain rule. Let's do one, maybe two more. You're going to need that table. Now, actually, let me go back to that table for a second. So realize this is integration, right? If you went this way on the table, what do you really have? That's the derivative. So the derivative of negative cosine of x is sine of x. Okay, so this table kind of gives you both, right? Okay, that's going to be important for the next problem. I already told you, got to look at the table. Everybody got the problem written down? Take something for you. You don't want extra on the side of you. Pick something for you. Any number. That's the tough part. That's the question. Pick one. There's two things in this problem that are annoying. One's gonna make your life easy, one's not. Uh, That's not. You literally are left to right. Pick something you- There's only a few things to make. It's kind of like a 50-50 shot. That's what it was. Actually, this is right. I think actually. Awesome. Okay, on this screen, where do you see something like what I got in the problem? This, right? That kind of looks something like this without the E. But there's some similarities there. Okay. That right there, remember sine of -1 of x is arc sine of x? They mean the exact same thing. Okay. So if I made u arc sine of x, what's du going to be? We just go backwards, right? It's 1 over the square root of 1 minus x squared dx. I'm going to go back to the other screen in a second. So all right. So u is arc sine. So this right here is that. Because I can rewrite this as e to the arc sine of x 1 over. So I have the integral of e to the u du, which is e to the u. So e arc sine x plus c. All right. We'll be done today. We're not done doing it.